All right, it's our last topic. You believe it? It is our last topic. It is multiple regression. It's not just univariate regression. We talked about last, but this is multiple regression. This is extra interesting. So, very often we're interested in simple one-to-one variable relationships. We talked about that on Thursday. And, you know, let's say, I think the first example here was what? IQ and income, which correlate nicely about 0.5. Fine. Let's say we have 0.5 for some relationship. Right? So our relationship says it's a 0.5 correlation between whatever our x variable and our y variable is. Remember, r equals the covariance of x and y divided by the standard deviation of x times the standard deviation of y. It's just a proportion of shared variance, irrespective of the scale. So, how much variance is accounted for by one variable in the other? In other words, how much variance overlaps? You have to, I said this the other day, you have to start thinking of variance as a thing you can pick, like an actual thing. It's an odd way to think. I understand that. It's strange to think of variance as something that you can hold. But try to think of it that way. I think it's useful. And it's how much of variance in y is accounted for by variance in x. In other words, how much variance do they share? Well, R deals with standard deviation. So let's square R and we'll get how much shared variance there is. Right? So in that case, R squared, little r squared, so 0.5 squared is 0.25. Okay. So what that's saying now is a quarter of the variance, or 0.25. So 0.25 of the variance in y is accounted for by variance in x. Okay? 0.25. It means there's 75% left we haven't explained. Explaining a quarter of the variance in one variable is an impressive feat. One of the things you have to realize about for example, personality psychology type variables. Personality psychologists are usually very happy when they can explain 9% of the variance, a 0.3 correlation. They get really excited about that. And that's fine. All I'm saying is that's explaining 9% of the variance in some variable. Explaining a quarter of the variance in a variable is very impressive. When you think about how complicated things are. So if you think about, and like I said, you can explain about a quarter of the variance in income by looking at people's IQs. There's still 75% left, but you're explaining a quarter of the variance, which is impressive on its own right, but let's explain more, right? We want to explain things. What do scientists do? What do we want to do? We want to explain how the universe works, even if the universe is some boring thing like IQ and income. So there must be other variables that account for the rest of the variance. There have to be. Because if not, we can just stop doing psychology. There's got to be some other variance, some other variable, or variables more likely, that account for the rest of the variance, right? What do? We do this by, we bring these things into the model. We bring them into the model. You know, sort of like we did the same sort of thing with analysis of variance. We bring in other variables. That's the same idea. So here's an example. If y here, and again we're thinking of variance as a thing, if this is the variance in income, and there's the variance in, we're going to say x1 is going to be the variance in IQ scores. And you see here's the overlap, and it's about a quarter. I don't know if that's exactly a quarter, but let's pretend that my Venn diagram is perfect. Is that a quarter? There's still a whole bunch of other variance out here in the rest of y that hasn't been explained yet. They don't overlap. So we could bring in another variable, let's call it x2, and let's say that's years of education. And then you're going to say to me, Dave, of course, years of education would probably also overlap with IQ score. You're right. Let's pretend right now it doesn't to make life simpler. It's going to get more complicated later, but let's pretend. So we've got now a variable y that we've explained with some of the variance in x1 and some of the variance in x2. Make sense so far? Questions? Okay. So again, this is the variance in the scores of x2, variance in x1, and variance in y, and they overlap some. All right. So in general, we have a model. Before our model, remember, was just y hat equals a plus bx plus e. Let's make it more general and say that we have y hat equals b sub 0. That's the same. Remember I said the other day, sometimes that you'll see it called b sub 0. So that's what our b, okay, right? Yeah, so it was a before, now it's going to be b sub 0. Plus b sub 1 x sub 1 plus b sub 2 x sub 2 plus dot 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 plus b sub p minus 1 x sub p minus 1 and e. P minus 1 is the number of predictors. There are p terms in the model, besides error, but there are p minus 1 predictors. So in our case, when we had x1 and x2, p minus 1 equals 2. But there are p predictors, right? Because b sub 0 is also there. It just doesn't have an x after it. So we have p minus 1 predictor variables. So this is for the data set itself. These are statistics. They are parameters. They're small Latin letters. So they must be statistics. They're not parameters, right? This is not describing a population. It's got y hat. It's actually describing something we did to a sample. These are statistics. So for statistics in the population, it looks like this. And here we get Latin letter, or we get some Greek letters. We get y, and it equals beta sub 0 plus beta sub 1 x sub 1 plus beta sub 2 x sub 2 plus dot 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 plus beta sub p minus 1 x sub p minus 1 plus e. Note that this isn't a prediction. This is saying how the universe actually works. So this model is for the population, and it's telling you this is how the universe works. The leftovers, the residuals, are normally distributed and dependent with a mean of 0 and a variance of sigma squared sub epsilon. That should sound extremely familiar. We say that about error all the time. As long as error is the big thing here typically is as long as error is independent, we're fine. If you violate that assumption, you're in real trouble. So don't. The normal thing you can not worry a great deal about. But the math, to make the math work behind it, has that assumption. Okay? So this is not prediction error here. In the model that's predicting a line, y hat, that's a prediction error. This is not an error. This is residual. This is leftover variance that we haven't explained with all these betas. Again, y, this is not a predicted y. This is saying this is how the world works. Which I realize is a subtle distinction, but it's an important one because in the population, we can actually make these statements. I mean, we typically don't know them. If we knew them already, we wouldn't have to collect the data to do the science because we know how the universe works. But theoretically, behind the scenes, that's what's going on. Okay. Questions for me so far? You okay? I know it's been a long time for a lot of you to do things with math, so don't feel bad if you have a question. Okay. So what we get, if p minus 1 equals 1, we get a line. In other words, if we have one predictor, we get a line. Like we talked about on Thursday, right? Simple regression, it's just a line. Y equals a plus bx, or really now we're going to be saying y equals b sub 0 plus b sub 1 x sub 1. Okay? That's more general. Now, if p minus 1 is 2, we get a surface or a plane. And let me use one of these old quizzes here. This is a plane, okay? So if we've got x, y, I think that right now there's no depth to this, not unlike myself. So there's no depth. Pretend that. That's a line, right? It's just a line, this part here. I don't want to get a paper cut. I got a tinfoil cut the other day. That's really bad. Don't do that. There we go. Now we get a new variable. So this is x1. This is y. Let's put x2 in. Now we got a plane or a surface. Okay? Does that make sense? Thank you, Mackenzie, for letting me use this. Though you didn't let me use it, I just did it. So we got a plane or a surface. Okay, I know you all did Cartesian coordinates in high school math, right? X, Y. Did anybody here do X, Y, Z coordinates? No, a little bit. Mostly a little bit, eh? I don't want to teach you anymore. Anyway, so it's the same sort of thing. If you did that, that's X, Y, Z, except we don't call it Z right now, the Z axis. We call them X1 and X2. And then 1, okay? So if you want to graph these things, you can. There are 3 graphing programs. I don't find them extremely useful personally, but some people like 3D graphs, and that's great. If p minus 1 is greater than 2, we get what's called a hyperplane in hyperspace, which is beyond 3 dimensions. Now the way to imagine this conceivably is we take Mackenzie's quiz, and it's a plane, and it's like that. Okay? Now, if the 4th dimension is time, it's moving around like this. Does that help you at all? Because it doesn't help me in the least. That doesn't help me visualize anything. My old stats prof, he used to say, it's easy, bro, but you just imagine it, it's moving around in time. And then, if you want to add another variable, is color. So what you do is you throw in like a dark color means low and a bright color means high. So it's moving around in time and changing colors. And I said, that helps you visualize data. He goes, yes, it does. I said, well, it doesn't help me. If that helps anybody in the room, that's great. I've never met anyone else other than Ian Spence, my old stats prof, who could imagine things like that. I guess if you really got into the graph, I don't know, I don't get that into graphs. He was actually really into graphs. It makes him sound really boring, the hell of a guy. I should use was, not past tense, I'm pretty sure he's still working. He was always around the beer keg at the graduate student parties. It was him and Gus Craig, the pretty well-known psychologist. They would stand by the beer keg. And they'd count how many beers he had, just for fun. They were having easily as many. But I think they had 17 beers. I think so too. Please get out of my way. Grad school's an entirely different experience than undergrad. And mostly in a good way. So hyperplanes, your best bet is not to try to visualize a hyperplane. To me, if it helps you, that's great. But I've never met a person other than Ian that it helped. So this is great, the one on the left. I think you can get an idea here. So here we have Mackenzie's quiz. It's a plane. And then here we have this is, I just looked up hyperplane on the internet. And it gave me that. Does that help anybody? Because it doesn't help me. Oh, the color changes. Okay, good. Yeah.
What does that color represent?
Well, I don't know. There's a scale there. Yeah, it doesn't help me. It helps some people. So in this case, the closer to red, the color. We're using the spectrum, right? Red, orange, yellow, green, blue, indigo, violet. RGBIF. Okay. So it looks like closer to red is a high score, closer to violet is a low score, I guess, in whatever the hell this is. I honestly have no idea what this is. And note the residuals here, these unpredicted points that are sitting out here in their different colors. It's wild. So don't try to visualize hyperplanes. And even, even planes on the left are not incredibly easy. Yes, there is more analysis of variance. Hinted at that pretty closely. Of course, there's more analysis of variance. Because we're going to look at variance here. Let's see if it's a significant amount of variance, right? So we can find out if the regression model we come up with is significant using ANOVA, because it's looking at shared variance. We're looking at variance with analysis of variance. Because it's called analysis of variance. So I guess that's what we'll do. So we have a couple of sources of variation. We got variance due to regression, that's the whole model, and variance due to residual. And in fact, many of you, well, I know you've all actually done assignment 3 that had you use the general linear model procedure to do analysis of variance. And you probably noted that it said model and intercept in the output. That's because, in fact, it's doing ANOVA with regression. They really, mathematically, are two sides of the same coin. They're very similar procedures at the deep level. So you get something like this. You got variance due to regression, and you get sum of squares for regression. Variance due to the residual, you get a sum of squares residual. And then you take mean squared regression divided by mean squared residual. Degrees of freedom p minus 1, number of predictors minus 1. N minus p, n is the number of records. Okay, so every time you have a data point, because I don't use the word data point, because it's a point, it's a record, right? So if you think of like a line in an Excel spreadsheet, or frankly, a line in SPSS, in a data set. So if you had like 200 records, and you had 3 predictors, this would be 2, p minus 1 is 2, and then n minus 3, well, n minus p, I said, what, 203, right? So you'd have 197. 197, 198, 199, n minus 1, 199. Okay. So this analysis is extremely crude. It's about the whole model. And it answers the question, and the answer to this question better be right. Does the model explain a significant amount of variance? And it bloody well better. If the whole model doesn't explain a significant amount of variance, you've wasted your time. You've got all these variables in there. This is never insignificant. It always will be. The question you want to ask here is, what about individual variables? Are they explaining a significant amount of variance? Because this is a thing, the regression model, that's the sum of its parts, literally. It's the sum of, b sub 1 times x sub 1, plus b sub 2 times x sub 2, plus b sub 3 times x sub 3, etc. So if that's the case, this regression model, is the sum of a bunch of parts, and we should be able to partition the variance and sums of squares and the degrees of freedom just like we would with analysis of variance. This is something we should be able to do, is to find out how much variance is accounted for by individual variables. So with our example with income and then IQ and what's the other one, years of education, we would look at how much variance was explained in income by IQ points, and how much was explained by years of education. Does that make sense? Questions? I know this stuff is not easy. I don't think this is the hardest stuff in the course. I think that power lecture early on is the hardest one, but this one's not easy. Okay. Well, let's do a finer grained analysis. So the model's going to be significant, as I mentioned, and it bloody well better be, but we're much more interested in how much extra variation is accounted for by adding another variable into the model. Because years of education and IQ, again, pretending they're unique amounts of variance, that's great. You know what else probably accounts for some very small amount of variance in income? Let's think of something. The number of earrings you wear probably has some very small correlation. I don't know what way it goes, but is it a significant amount? Probably not. Because everything's going to correlate at some level. The question is how much variance overlaps. It would be so small that you wouldn't want to use it. Is it extra variance? Yeah, who cares? It's so small that it doesn't matter. Right? It's so small it doesn't matter. In that case, so would we want that in the model? Probably not. You'll lose degrees of freedom. You want the simplest possible model that explains the most possible variance. Oops, okay. Must move this here. Here we go. By the way, remember we talked about little r squared. We can get what's called big R squared, which is sum of squares regression over sum of squares total. And that's going to tell us how much total variance is explained. It's a proportion of variance explained by the model. That's called big R squared, and you'll see that in outputs if you play around with SPSS or something doing regression. Okay. So if we're going to add variables in, if we have a variable with 5 x variables, so we got x1, x2, x3, x4, x5, and we add in a 6th variable, does r squared go up? Well, it has to. Because, and again, thinking back to the sort of Venn diagram idea, and we've got some overlap, every single time you add something in, it conceivably could stay the same. It could. Because there could be 0 correlation, but any small amount will make r squared go up. When you add an extra one in. Variance it's no way to go down. But the question is, does it go up by enough that we care, right? So this is what I like about regression in some respects is that there's a lot more judgment of the scientist involved here. There's a lot less of, oh, that's not significant, we're done. Which we're getting away from. We're sort of getting towards now exact p-values. We're doing the same, regression's been doing that for years, which is the scientist, the data analysis person looks at it and says, is that enough extra variance that I care? And they make a judgment call. So the question you always ask yourself is it enough to deal with the loss of degrees of freedom and the increase in complexity? Like if you're going from a straight line to a plane's harder to imagine, but you can take up Mackenzie's quiz and do that, and you can imagine a plane. Hyperplane's not so much. So if I'm going to go from 2 predictor variables to 3, that's a big step for me. Because I can't draw the thing anymore. One of the nice things you can do in an article, in a paper you write, in a journal article, whatever, if you can draw a picture for the reader, that's great, right? Because pictures are apparently worth at least 1,000 words. Though I think with inflation, it's like 1,020. Thank you. Thank you very much. So, but I can't draw a picture of a hyperplane that anybody understands. I guess I can probably have some software draw one, but no one's going to understand it except Ian Spence. So if you're giving something to Ian, that's great. I tried to draw a 3D graph once in a classroom. And I couldn't do it. I literally, that was it was a quiz. And part of the quiz was draw a graph of this hyperplane. I can't do that. So I wrote a little thing saying, I can't do this because I'm blind. Which was obviously I was kidding. And he wrote, I don't care, which was just awesome. Again, it's graduate school, it's a different relationship. We were very friendly. I was his TA. And I was kidding when I wrote that. I don't care about that. That was great. I learned almost everything I knew with statistics from that guy. Almost everything. So that's extra complexity. I don't like complexity. I like simple things. I am but a simple man with simple tastes. I don't even need imported foie gras. I don't think any. Nothing. Foie gras is pretty good. All right. So we need something other than R squared, because if we just look at R squared, it's going to keep going up. Here's something, I would never ask you this. I'm telling you this exists. This is not going to be on the final, and frankly, if it was, here it is right here. This is a thing called adjusted R squared, and it actually can go up and down, because note it's weighted by the number of predictors in the model. Because P's in there. That's nice. That's a little easier to deal with. This actually can go up. So it's adjusted R squared. So that's somewhat useful. That's somewhat useful. Okay, here's something theoretical. I'm going to show you three sort of theoretical models. Tell me which one is the best model. So this is just with x1. Sum of squares regression is 50. Sum of squares residual is 80. Let's put that one over here. x2, that's just x2 in the model. That's got sum of squares regression of 30 and 100. So just with these two, which one is better? Well, it's this one. This is explaining more variance. This is explaining 50 variances, and this only has 30. So without any extra information, with just this information, you can tell me right away, I would prefer the model on the left. Just x1. Now, of course, there's also an intercept. So this model here would be y hat equals b sub 0 plus b sub 1 x sub 1 plus error. This one here would be y hat equals b sub 0 plus b sub 2 x sub 2 error. There's different variables. So when I say the x1 model and the x2 model, I'm assuming, obviously, that there's error, very clearly, it's residual. And also, there's always an intercept. There is a kind of regression you can do to force there being no intercept. It's not really worth our while to worry about. What about using x1 and x2? Whoa, there's a new one. It should be centered. It's not. Oh, well. So the question I have for you, with all three of these models, is which one is the best? There is a wrong answer, and there's perhaps more than one right answer. The wrong answer is probably this one here, this next two, because it explains not a whole lot of data, not a whole lot of variance. And I think, to me, I'd say that there actually is a right answer to this. Yeah. To me, the best one is the two-variable model. It explains a lot of variance, and it's not that complicated. It's still just a plane, so I can still visualize it. I can have software draw me a picture, right? Here's a question. Do x1 and x2 overlap? In other words, are they explaining any of the same variance in y? So look at the numbers. Look at the numbers. All right, the x1 and x2 overlap. So do they look like, at the beginning when I had the y, and x1 came in and x2, and I said, oh, well, x1 and x2, I guess, don't overlap here. They're explaining unique variance. Are x1 and x2 explaining unique variance, or do they overlap? And why? This is a really good exam question. Though it will be a little more complicated. Thoughts? Who has an idea? Go ahead.
Well, they seem like they're separate because they're adding to 80 on the right.
Yep. They're separate. This accounts for 5. Well, what's the total? There's a couple things to note. First of all, notice how the total is always 130. Because that's the total amount of variance in all of the data set. So that's great. So it's always going to add up to 130, and it doesn't. This explains, x1 explains 5/13 of the data, of the variance. x2 explains 3/13. And x1 explains 8/13. And notice how 80, as Evan said, is 30 plus 50. If these things overlapped, if x1 and x2 overlapped, this would be less than 80. It could never be more than 80. But it could be less. And let's think about this let's think of a ridiculous example. Sometimes ridiculous examples can be extremely instructive. So let's grab a marker here. So here's y. Now, I'm sure this is out of, that's going to be x2 because that's closer to that. Here's x2. x1, they can't overlap because, let me make it so let's say that's x2. They don't overlap because this here is 30, and this here is 50, and these two together are 80. Let's think about this. Now, as I said, now let's think about the absurd example. Here's y. Here's x1. The color. And let's say y in this case is what? Let's make y height. And we're going to make x1 your weight in kilos, and x2 is your weight in pounds. They completely overlap. So in that case, there'd be no difference between x1 and x2, and they'd also do the same thing with x1 and x2. But that doesn't happen very often. Okay. Did that make sense? This is kind of a key thing. Oh, good. I think. All right.
So Dave,
Yep.
the whole point of all that
Yes.
is just explaining the variance.
That's all we're trying to do is explain variance. Yep.
Okay.
Yep. So if I want to predict something, I want to explain all its variance. So if I want to predict, anything, I'm literally trying to explain variance. That's what I'm doing. Where does the variance come from? And I can make a nice equation and tell you. Yeah.
Big picture
Yeah.
attempt.
So I talked the other day about type 1 and type 2 sums of squares. Type 1 sums of squares depend upon what, and this is for regression. It's also true when you do analysis of variance with regression, and spoiler alert, all your software is doing it through regression. It just doesn't tell you that. Type 1 sums of squares depend on the order the variables go in. Type 2 don't. So let's say we have a 3-variable model, x1, x2, x3. So we've got 3 possible predictors. 3 predictors. So the type 1 sums of squares, the sum of squares regression for x is it's just x1. When you see what the sum of squares regression is for x2, it's actually both x1 and x2 in the model. Type 1 for x3 is x1, x2, x3 in the model. That assumes we did the analysis in that order. I know it's kind of odd to think of, but that's all it's doing. On the other hand, type 2s are conditional. x1 given x2, x3, x2 given x1, x3, x3 given x1, x2. So what these are conditional, and they're type 2 sums of squares look at unique variance. So the thing you care about a lot, type 1s actually have a use. Don't have to worry about it right now. The important thing is type 2s, because what type 2s do is they tell us how much unique variance is accounted for. That's a big deal. Because if something accounts for, if we had the height in centimeters and the height in inches, or whatever the hell I said, no, I think I said weight in kilos and weight in pounds. If we had that, it would say that we had no unique variance. Right? So we're going to end up looking at type 2 sums of squares. And again, this is done automatically. We have our software do this for us. Right? It's funny because these videos are on my YouTube channel, it then of course suggests things. And one of the things that, most of the things that are suggested to me are fixing retro computers and things about TV shows. That's what's usually my suggested list. And then the other day was how to do multiple regression by hand, and I thought, you poor bastard. I mean, if you want to do it by hand, you go nuts, buddy. Not me. But if you're listening to this, whoever made that video, good on you, buddy. I wouldn't do this by hand. I don't know if I could do it by hand. I probably could. Yeah, I probably could. I wouldn't want to. I guess you could ask me, why should I care? And my question is that my answer to you is because this is a required course. But also, if there's no correlation between any of the variables, if there's no overlap, the type 1s are equal to the type 2s. Beautiful. If there is a correlation, if there is overlap, type 1s are not equal to type 2s. So that's right away one way you can look and go, okay, when I do the type 1s, type 2s, type 3s, type 1s and type 2s rather, do they show they're the same or not? And if there is a correlation, type 1s are not equal to type 2s. We'll get a bit more on that later on. So what do type 2s give you? Type 2s give you the extra variation accounted for by having a variable in a model given the other variables are already there. They give you exactly what we want. How much unique variance is accounted for. This is exactly what we want. So this is the quantity we're interested in. And when we figure out do we want to put a variable in a model or not, we're going to be looking at type 2 sums of squares. Okay? We'll be looking at type 2 sums of squares. And this can also give us something called the coefficient of partial determination, which is somewhat useful. It allows us, it's sort of like big R squared, but it's little r squared. And we can actually take the square root of that. It's called a partial correlation, which you may have seen in articles you've read. And it's really just a correlation, little r, sort of little r squared, and then we take the square root of little r. And you can see like extra variance accounted for, assuming something else is there. It's maybe like statistical control. It's kind of cool. So big R squared is the coefficient of multiple determination. Little r squared is the coefficient of partial determination. So here's a picture. So there's all the variance in the Y. I find this is the most, regression is the place where I use the most pictures to understand things. And in fact, this is how it was taught to me, so I can understand it properly. Because this is, again, mathematically, it's non-trivial, at least to me. So there's all the variance in Y, and there's the variance in X1. Notice how X1 accounts for some of the variance in Y, there's some left over. And now here's X2. That's great. They don't overlap. We're fine. Now let's think of, this is the ideal world where two variables don't overlap. So X2, X1, X2, it's going to be a nice model. It's explaining a lot of variance, no overlap. Now, in this case here, we've got, again, X1 same amount, it's supposed to be exactly the same size. If it isn't exactly the same size, it's supposed to be. Now let's throw x2 in. Oh, notice how it just wrote over some of the x1. In other words, they share a lot of variance, x1 and x2. I've not explained a whole lot of extra variance by adding x2 in. In fact, I've explained hardly any extra variance by adding x2 in the model. It really overlaps a lot with x1. On the other hand, if we started with x2, we would say maybe x1 is not a very good variable. That's why we don't just look at type 1 sums of squares, we look at type 2s. The type 2 here would be very small because the extra variance accounted for would be quite small. Okay, whoa, that went the wrong way. That was interesting. So the coefficient of partial determination, that thing to measure that extra variance, is an actual, like, it's not just look at a picture, but it's a mathematical or a numerical representation of how much extra variance we've actually accounted for. You can square it, and as I said, get the coefficient of, of partial correlation. No, take the square root of it and get this partial correlation, not the old square it. I gotta fix that. Take the square root. That's a hell of a mistake, Dave. Square root. Questions? Okay. Now what is this method? Let's think about the model. And this is our model. This is for the statistic, y hat equals b sub 0 plus b sub 1, x sub 1, blah, blah, blah. That's our model. There's nothing in there about how two variables overlap, is there? Do you see any terms in here that have x1 and x2 shoved together? No, you don't. There's nothing in there saying, oh yeah, and also there's nothing overlaps. The model explicitly says it's additive. It explicitly is saying that these things are separate. There's nothing, so that's just going to make this bigger. Make error bigger. This thing, when we have overlap of predictor variables, is called multicollinearity. And multicollinearity can be a real problem because you're adding variables that don't explain any extra variance or don't explain a lot of extra variance. But they're making your model more complex and you're losing degrees of freedom. Okay. So actually what you're doing there is you're violating an assumption. So what happens if you violate an assumption? The b's, those b sub 0, b sub 1, b sub 2, those are the really important things because they're coefficients. They're going to, you multiply those times the x values to get some number. The other day we talked about how, I don't know, if you wanted to think of the salary floor as, what's the word, the intercept, and then x is the number of years you've worked here, and b is how big your salary steps go up. So it's like that. It's the b's are what comes out of this thing. So the b's are going to change. How do we detect multicollinearity? Well, one of the ways is by looking at type 1 and type 2 sums of squares, but the easiest way, frankly, is just to do a correlation of every possible variable. So you get a data set. You don't do this on small data sets. You don't do multiple regression on data sets with 3 independent variables and 20 records. You don't. You do it on data sets with 500 records and 30 variables, things like that. And in fact, there was a time where there was a fifth assignment. I cut back on the assignments a few years ago because it didn't seem like it was helping any and it was just making everybody the same. So I thought I'm just going to go back by one. But the old assignment, the old final assignment was, here's a data set and a real data. I told you about that smoking data, correcting how much people smoke. I have the data that a friend of mine collected back in the 80s. And it has 500 records. It has 23 possible predictor variables and 1 predicted variable. And I just tell it the assignment is as follows: find the best model. That's all it was. Don't have to have fun. Which is not trivial. It's not an easy thing to do if you haven't done it before. It's like, I don't know what they're getting out of this, so I stopped doing it. But the first step you would do is you would take all those predictor variables, all 22 or whatever they were, and see if they correlate with each other. And ones that correlate highly, you got to be a little suspect, right? Suspect? Why did I pronounce it like that? You got to be a little suspect. Put the accent on the wrong syllable there. Little suspect? You suspect someone. Okay, this. Huh. So you look at a correlation, you can see, oh, these two correlate pretty highly. I probably won't use that. Use one of them. You might have to chuck a variable. You got to get rid of it. You say, I'm sorry, I can't use this variable. And if I remember correctly, two of the variables in that data set that correlate pretty highly are maximum number of cigarettes per day and minimum number of cigarettes per day. They correlate pretty highly, which you would expect. And the smart move in that case is to get rid of one of them, and the one you get rid of, I think, the way I would do it is I would look and see which correlates with Y, which is cigarettes per day, and the one that correlates the less, you just get rid of it. Don't use it. We also assume a linear model. Now, we think about straight lines, but we got hyperplanes and stuff. It's not straight. They're not lines anymore. But in any case, what you have is a model where it's this times this plus, this times this plus. They're additive. They're linear. There's no terms in there that have exponents. There's no terms in there that have two things multiplied times each other, except for beta weights, which are those slopes, basically. But you have no. There's nothing multiplicative about the model. What if the model is nonlinear? There's a lot of functions, though, that are nonlinear. You can think of, exponential functions, which we've learned a lot about in the last 2 years. We can think of parabolas. Think about the most recent quiz. We had the upside-down parabola. Let's pretend, I'm never going to ask you how to do this. I'm just giving you an example. So let's say that y equals, what the hell Greek letter even is that? Is that a lambda? I think that's a lambda. Is it?
Yes.
Okay.
If I'm wrong, you'll know if on that one.
Lambda sub 0 to the lambda sub 1 times x times e. Let's pretend that that's actually the way the universe works with some variable. You look at that and you think, well, I can't do regression on this data set because it looks like it's like this. The thing is, you could actually turn that into straight lines. But first you scream, ah! Then, just take the logarithm of the thing, then it ends up, it fixes everything. So log y, log lambda sub 0, log lambda sub 1, x sub 1, etc. And if you remember from high school, when you would giggle when your math teacher would say, well, now you can drop the logs. You don't go, because you're idiots. I think she means poo, because you're an idiot. Okay, maybe this was just me. Maybe only I learned the logarithms in high school too, which I find disturbing. But anyway, that's actually what's called an intrinsically linear regression. So that's something where we can actually transform it. You have to know I shouldn't say a great deal. You have to be very conversant with graphs and different functions before you can look at something and go, oh, that's an intrinsically linear regression. I can figure that. But there are times when it's true. So in fact, if it's the case that you have some weird-looking relationship, and I don't mean in your personal life. I'm sorry, I was looking right at certain people. I didn't mean it that way. Some of these jokes are so just for me, it's obviously. And some of them clearly aren't jokes because nobody's laughing at them. Still, I think I'm a comedic genius, and I'm sticking to that. If you might look at something and go, what's going on here? It looks like I can see a shape. It doesn't seem random. There's a shape here, but I don't know what the shape is when you look at a scatter plot. That's when you go to talk to somebody who knows about this stuff. And you don't have to ever feel bad about that. You go talk to a mathematician, talk to a statistician. That's what their jobs are. Well, their jobs really aren't just answering questions from students, but partly. So that's called an intrinsically linear regression. It might not be linear. Not everything is linear. Like sometimes you look at something that looks, oh, that's great. I don't know what that shape is. So maybe you just write it Jeremy Baramy. Anybody? A good place? Nobody? Nothing? It's a good show. So it might not always be linear, but this is actually that weird exponential equation is actually intrinsically linear. You can turn that into a linear equation easily. So if you think about some of these things like, exponential growth functions for viruses, they're actually, you can turn them into linear equations. You just take the logarithm. It's trivial. It's very simple. So we're assuming an additive model. There's no mention of interaction. So think about, with analysis of variance, we had alpha, alpha, beta, and alpha, beta. We don't have that here. You could try saying, oh, we got, y hat equals b sub 0 plus b sub 1 times x sub 1 plus b sub 2 times x sub 2 plus b sub 3 times x times x1 times x2. You could put that in. My question to you is, how do you know that it's just those two things multiplied together? You can do that. There's nothing stopping you. But you have to be pretty darn sure of what you're doing. There's nothing about interactions in the model. One of the big differences between multiple regression and analysis of variance is that we can't really deal with interactions with multiple regression. There's a lot of differences between regression and analysis of variance. There's a lot of similarities, by the way. In fact, asking you what the similarities and differences between multiple regression and analysis of variance would be a really good question for a final exam. Like a really good one. Like a really, really, really good one. Just saying. If you did have a final exam coming up, that would be something I would know. Was that clear enough? Okay. It's tough to know what that term is going to be, that interaction term. I guess exploratory data analysis can tell you. You could look at something and say, yeah, okay. But it will be hard to know. So any questions? We'll probably stop here. All right. So, as we were talking about last time, or if you're watching this on YouTube, merely seconds ago, so predicting, we're picking our predictors and for a model, and we're looking at the assumptions of the model of regression in general. So there's no mention of interactions, and I mentioned this, as I said, of course, just moments ago on YouTube or 2 days ago in class. So you could always put something in, x1, x2. Hard to know what that term should be. Exploratory data analysis might be the key. It's often the key. I think I've been harping on that since day one. So let's select some predictors. So, in other words, these are the x variables. What variables do you want to use? These are the x variables. So, do you want to have qualitative things? So we can use qualitative variables all the time in an analysis of variance situation, right? Group 1, group 2, group 3, doesn't matter what the 1s and 2s and 3s are. It's a little more difficult here because we're building an equation. So how are we supposed to? Let's say we're using hair color. Let's just make it simple and say there are 4 hair colors. Blonde, brown, black, red. And I know it varies and blah, blah, blah. And yes, you're all very special. Life's a rich tapestry. But let's say we have 4 hair colors, okay? To just make the example easy. How do you code that? Like, you're going to try to build an equation. How are you going to put what number is red? I don't know. That's a hard thing to code. If it's a binary thing, it's easy. So if we were coding, I don't know, psych students or not. Well, you get 1 if you're a psych student, because your level of psych studentness is 1. And then if you're not 1, 0, because you're 0 of a psych student. This can give us a hint as to what to do with other qualitative variables, like, let's say, hair color. First of all, you're going to code this, as I mentioned, 0 and 1, not 1 and 2. It's very tempting for some reason to code things as 1 and 2. And you wouldn't want to do that because a psych student is not twice the psych student that a non-psych student is. Right? The numbers have to mean something. So, but 1 and 0 actually makes sense. So this can give us a hint actually of how to deal with a qualitative variable. Let's say like hair color. What we can do is we can do what's called dummy coding. And do a quick picture of that. So if we were just doing hair color and we were doing something that wasn't involving building a mathematical, well, not a mathematical model, but an equation, we would just use brown, black, red, blonde, and easy. We can't do that. So instead, if we have 4 hair colors, let's have 4 variables. We'll have a variable called brown, and a variable called black, and a variable called blonde, and a variable called red. Now, how do you code someone's hair color? So subject variable, and the first subject will be me. I do not have brown hair, I do not have black hair, I do have blonde hair, I do not have red hair. So now I've got 4 variables. So I'm 0, 0, 1, 0. Because I have 0 on black, 0 on brown, 1 on blonde, 0 on red. Okay? So if somebody had red hair, we'd go 0, 0, 0, 1. If someone has brown hair, we go 1, 0, 0, 0. Black hair, 0, 0, 0. Make sense? So this is a way we can actually get around this. It's actually, I don't know who came up with it, it's very clever. It's very clever. And for some reason, when this was taught to me, I couldn't get my head around it. Like I really couldn't. I sat there staring at it going, I don't understand this. But I'm supposed to be the kid who knows statistics, don't put your hand up, don't ever act like that. Does everybody get this, is what I'm asking you. Because I didn't get it when the first time it was taught to me. Does that make some sense? So you're saying I'm a better teacher than my stats teacher. Freaking right I am. Okay. Or you're all smarter than I am. I choose to believe not that. But I'm a great teacher and I'm smarter than all of the people. So, that's a joke. I'm smarter than most of them. You guys know I'm kidding around, right? It's hard to tell with the mask on. You can't see the sarcastic look on my face as much, I guess. Okay. So that makes sense? It's very cool, actually. In fact, yesterday, I had a meeting with one of my honors students, and she was putting her data together for analysis, and she had done dummy coding, but she shouldn't have. It was really kind of funny. I was looking at her, and I was literally looking over these notes, and just before talking to her, because I know, oh, this is coming up, and I was looking at it going, no, that's right. Oh, that's right, that's right. No, it's wrong. You don't need to be dummy coding what you're doing. She's not building a regression model. But I got just confused. I was looking at it. I'm sure that gives you a great deal of confidence in my ability if I just look at something confused after I've told you that I didn't get something I'm now teaching you. Probably I'll ask you for your money back afterwards. Watch out for Likert scales. Psychologists, behavioral scientists in general, we love Likert scales, don't we? Right? 1 is strongly disagree. 7 is strongly agree. 4 is neutral. On a scale of 1 to 7, we love that stuff. And we treat it like those numbers, like the gap between 1 and 2 is the same as the gap between 6 and 7. I'd be really careful in using a Likert scale in a regression model. You can do it, but you better be damned, it better be very defensible that the differences between the intervals are the same size. And that's a hard thing to know. Okay, that make sense? All right. Experimental variables can be great. There's never going to be any multicollinearity between 2 variables that are 0 and 1, and you assign them. So if we had a case where we've assigned people to groups. And we can actually look at the numbers, and we have numbers that are meaningful. Then it's great. We can use an experimental variable. It's wonderful. Because we can be sure that people can't have level 1 and level 2 of A. So that's wonderful. Now you wouldn't again go 1 and 2 unless those numbers are meaningful. You'd probably code it as zeros and ones. Okay, questions? All right. So what we're going to do eventually is build a model. We're going to build a mathematical model, a regression model, that's going to predict our Y. That's what all we're trying to do. So how do you choose the variables that go into your model? Because you might have, I mentioned the other day, 23 variables, and you don't want a 23 variable model. That's kind of complicated. You probably want something, I don't know, 4 or 5 variables max, typically. How do you choose which ones to use? So this is much different from analysis of variance. We're actually making a prediction with multiple regression. And we're saying that the world works like this, that a combination of this and this and this and this and this equals this. That's not what we do with ANOVA. What do we do with ANOVA? We try to find out, is there a significant effect of a variable? Right? That's not what we are doing here. We're trying to say all this together is it a useful way to predict something. There are obviously related questions. Because you usually start out with a lot of variables. Within an ANOVA situation, you might start out with, say, 3 independent variables, or 2. You know, if you watch the honors thesis conference, there'll be 2 meetings of that, not next Friday, but the one after and the one after that, if I'm not mistaken. And my students, 2 of them have 2 variable designs, and 1 has a 1 variable design. I like simple designs, and they're all analysis of variance. Sorry. 2 of the 3 analysis of variance, 1 chi-squared. With regression, you might start out with 20 or 30 or 50 variables. And you want to break, get down to the point where you say it's a combination of these 5 or these 4. Well, the first thing you could do is you could literally do all possible regressions. You could literally look at every single conceivable model. Sure, so with a 3-variable data set, so you've got an x1, an x2, and an x3, there are 7 models. There's 3 1-variable models, right? x1, x2, x3. Then there are 3 2-variable models, x1, x2, x2, x3, and x1, x3. And then there's x1, x2, x3. Yeah, 7, I got it right. There's 7 models. That's not so bad. I can look at all 7 and go, which one's the best? That's easy. If there's 4 variables, it's 16. That's even still doable. That's going to be a lot of, and you know what? As much as I like doing things on screens, and I've got, I think many of us now have dual monitor setups at home and all that stuff, this is a situation where I use paper. Maybe it's because I'm old, but it's hard to look at that many things at once when they're on screens. I prefer having it paper and literally spread out on the floor. I suddenly look like, I'm on some TV show. That TV show Numbers, remember that show? The guy used math to solve crimes? And you probably don't, right? We're small children. It's a good show. He actually used multiple regression in one episode, and I loved it. It's like, oh, look, he's what he's doing. I know that math. Now, with 10, I don't know how many there are, but let's say it's a zillion. And I told you the other day that an old assignment I used to use was give people a 23-variable data set, and I'd say, find the best model. And I also would always say to them the same thing, please don't do all regressions. Because you're going to run out of everything. Computer time, paper. And the first time I used that assignment was in 1992. I was a senior grad student, I was teaching this class at U of T. And because this class exists everywhere. And yeah, I said to them, now specifically, everyone, please don't print out all the possible regression models. You will hang the entire U of T computer network. So guess what like half my students did? I kept getting these calls. Can I speak to Dave Broadbeck? Yeah. This is the computer lab in Sid Smith Hall here. Your students, oh, don't tell me they're doing that. Yeah, some of them are trying to print them all. Okay, can you kill the genome? And of course, the guy who killed him and everything, he was just warning him. And he said, okay, now that shouldn't happen. I said, no, it shouldn't happen. I'm not actually stupid. I told them not to do it specifically. Then, like 2 days later, is this Professor Bright? I said, yes, I'm just thinking. Well, your students are printing. I said, I know, tell them to stop. I told them not to do it. It's impossible. It's trillions of possible models. I calculated, I figured this out one day, and if you did like 1 a minute, it's longer than the amount of time that there's been Earth. You can't. It's something crazy. For the 23 minutes. So what do you do? Well, the first thing you can look at are residual plots. These can be very useful. So this is all exploratory data analysis. You can find anomalies with residual plots. So you can do a 23 variable model, just put them all in, that's fine if you feel like it, just say, don't say, and all the other ones as well. And then say, you say to SPSS or SAS or R, or whatever stats package you're using, you say, and give me the residual plots. And it'll do that, that's always an option. And look at them and see if you see anything weird, like a weird anomaly, like you get one point that's way up here. Or you've got a curve, or like a cone, so it's, the prediction errors get bigger as the X variable gets bigger. Those are bad things. Nonlinear relationships, you're probably going to have to drop that variable. Like, okay, here's, I think, in fact, these are the same things I posted in our study group. This one here looks fine for x1, right? This one here for x3, as x3 gets bigger, the residuals get bigger. They should not be related at all, those two things. That's no good. Here we've got, obviously, it underpredicts and it overpredicts. That's no good. And then finally in the bottom right here, we've got a curve. You don't want a curve. What you want is the top left there, x1, which is something where you don't have any relationship between the residuals and the x value. Okay? And remember, there are 2 questions in the final about residual plots that involve literally looking at residual plots and interpreting them and saying, is this okay or is it not, and what's the problem? So again, starting from the top left, that one's fine. This one here, prediction error increases as x increases, no good. This one here, underpredicts and overpredicts, no good. This one here, underpredicts, overpredicts, underpredicts, almost certainly a curve, no good. So these are 3 variables, x3, x2, and x4, we wouldn't even use. We would throw these variables out if we're building a regression model. They're perfectly fine variables probably, but they aren't good. They heavily violate an assumption of regression here. That's not good. Make sense? Yeah? So one of the ways you can do this, you're thinking, well, we have computers. Why don't we let a computer do it for us? Why don't we have some kind of algorithm that builds a model for us? That'd be great. Yeah, let's do that. So there's a few algorithms I'm going to talk about. And these are all available in any stats package. So this automatic method or algorithm is called forward selection. And what it does is it starts with the x variable that has the highest r squared. In other words, it looks at the variable that explains the most variance. And it says, put that in the model. And then it keeps doing it. And then it adds the next variable that gives you the next biggest jump in r squared. Okay. You keep going until the jump in r squared is not big enough. And you're saying, that sounds very vague, Dave. Yes, it does, doesn't it? Because it is. Typically what I do is I just leave it to what the statistics package has as a default. And I go from there. How does the statistics package measure the biggest jump in r squared? Well, r squared is just a number. It's just a variance estimate. Oh, look, it's our friend the f-test. We're going to look at mean squared regression for x1 given x2. divided by mean squared regression for x1, x2. In other words, type 2 divided by the type 1, they'd be some mean squares. I've never asked you this on a quiz or anything. All I'm saying is what it's showing is this is a proportion of total extra variance explained. That's what this is measuring. And when that's small enough, it's called F star, because that's the asterisk. Gives it that. If that's a big enough jump, it keeps going. Once that F star gets below a certain significance level, it stops. And then it spits it out. So here's your model. Okay. Let's do it the opposite way. Here's another algorithm. Does the opposite. It starts with all the variables in the model, so it literally does exactly the opposite. Take all the variables. So if it was that 23 variable data set, they'd all be in there, and it takes the one that has the least, the smallest R squared, and just takes it out. And it just keeps going. In other words, the smallest F star. And it just keeps going until it hits some threshold, until it's like, oh no, you took that out, that's too much. And it stops. It stops. Okay. Now, what if we could combine the two into something? Well, obviously we can. I've got a slide, I just said it, and you've got a name. It's called stepwise regression. You'll even see this sometimes used in papers. People will say, we use stepwise regression. No, you didn't. That's not, it's an algorithm, it's not a statistical analysis technique, and it drives me up a wall when people write that in their papers. It's like saying, and I've seen this too, we used SPSS to analyze the data. I don't care. So if you do it by hand, you're supposed to say, I did this myself in my head. No, of course. Anyway, that's an aside. So stepwise is interesting because what it does is it combines the two, which sounds good. It's going to be the best of both worlds. It goes forward. It starts by going forward. So it puts the one with the biggest R squared in, and it checks F star for each variable. So once it's got just one in, it says, okay, that's good. Now it's going to pick the next one. Now you get two variables. The neat thing that it does now is it then drops variables. So as, say, 2 come in, then it looks at this. If I take one of these out, is that okay? No, that takes away too much variance. Okay, add a third variable. Now that I have all 3, if I take one of these out, is it okay? Is it still okay? No, let's put a 4th one in. Good. Let's put a 5th one in. Oh, now if I drop actually that 3rd one, it's still good. So what it's doing is it's adding variables and removing variables as it goes. So each step adds or removes a variable. And there's a criteria set for adding and dropping. It's called the F to enter, or F star to enter, and F star to leave. Now the thing is, this is one of those cases where, again, probably messing with this is a problem. There's usually a default set. I wouldn't change the default in the software. F star to enter has to be greater than or equal to F star to leave, or it's going to get caught in a loop. It's going to put a variable in, take it in, put it in, take it in, put it in, take it in, and it will stop. And this is something else that my students did at U of T. And literally hung up the entire U of T mainframe network in for the social science. Basically for arts and sciences at U of T, all the computers were completely held up. They were different time, early 90s. Just don't mess with that. The thing is about these approaches, these automatic approaches, they only look at F's. They only look at F to enter, F to leave, whatever. They're looking just at variance. They're not looking at residual plots. And I bet now that people are working on algorithms that actually can do this. They aren't available in regular stats packages, but I'm sure people who are smarter than I am can do such things. But these methods that are sort of standard things, forward selection, backward selection, or stepwise, and most people go with stepwise, They don't tell you anything about the variables other than how much variance they're accounting for. They don't care about multicollinearity. They do indirectly, because if something doesn't add much because something it overlaps a lot with another variable, indirectly that's looking at multicollinearity. But they actually don't look at it. They don't worry about it. Is the relationship linear or not? Nope, they don't care. They don't look at that. They can't. They're simply looking at F to enter or F to leave or both in the case of step one. So they're perfectly fine, but they aren't the be-all and the end-all. As my old stats prof, and I've told you about it many times, Ian used to say, these methods will give you a model. They probably won't give you the best model. They will give you a model. It could be the best model, but usually it won't. Usually it'll just be a model. Here's an approach, and I've done this. I don't use regression very much, but I have, and here's what I've done. The first thing is I would start out with a correlation matrix and see if there's any multicollinearity. So do any X variables, any predictors, do they share any variance with each other? And if they do, I will want to rid of them. One of them, probably the one that has the least correlation with Y, I'll get rid of. So I pick a subset of the variables that don't correlate too much with each other. And if, in that case, if I've got, let's say, five variables or 4 or 3, I'd probably just run every possible regression. Because frankly, at that point, I can deal with 15 or 20 models. It's annoying, but I'll see them all. Right, so I can look at residual plots, is anything nonlinear, and that's easy. If it's bigger, even if it's not big. So I will take my subset, I'll also try all the automatic methods. I'll try all 3, forward selection, backward selection, and stepwise regression. Or, if the subset's pretty big, I'll do that as well. I just can't do the look at all possible models. Let's see if they agree. They don't always agree, by the way, these algorithms. They literally don't always agree. Which is kind of wild when you think about it. As I'm going, I'd be checking for outliers on residual plots, I'd be checking for curves, things like that. And then I'd put it away for like a week and do it again and see if I get the same result. This is just me. I'm not saying this is what you should do, but it's an approach that is, I'm checking myself, because there's no way I'm going to remember every step a week later. So I put the data away, I put this, it's like, I'll come back to this in a week, I'll do other work. When I come back to it, do I agree with myself? Because, you know, as I think you can see here when we've been talking about today, there's a lot of real judgment calls here. There's not, oh, P is less than 0.05, done. There's a lot less of that. Right? Okay. Look at that, that's the conclusion slide of the last topic. Right? Right? This is an extremely powerful technique, regression. It's an extremely powerful technique. Think about this. I can take a bunch of data and I can say, I put all these things together and then I can say I can predict Y from this combination of X's. That's a pretty powerful technique. Watch out for multicollinearity. This is the thing a lot of people miss, is the correlation of their X variables. So watch out for that, please. Try not to violate the assumptions, and the assumption's not so bad really here. Basically, it's linear relationships, and that the residuals shouldn't be related at all to the x values. Those are the key things. Try not to violate the assumptions, you'll be fine. And just because it's an equation, it's very tempting when you see an equation, like I just said, right? Ah, I'm saying this plus this times this times this, and this plus this times this plus this times this equals that. It's very tempting to say, so therefore, that causes that. That's not what you said. All right? It doesn't mean a thing. Just because it's an equation, don't assume you proved causation. It's extremely tempting when I see this equals this to say, oh, that means that causes that. Doesn't mean that. There's probably some causal connection. But remember, this is really a correlational technique, typically. And because of that, there is no assumption in any of the math that we've designed an experiment here. So that's about experimental design. That's not about stats. Any questions? Good. Pretty cool. Actually finished the course. Now, we have two possibilities here. I have some slides that are a review that wrap things up, or we can save that till Tuesday. We can still do review Tuesday. It only takes about 10 minutes, but it's just a thing of some slides. You want me to do it then? Because I can.